Okay, so now that my finals are over, I can kind of get back to working on some videos. And we're actually going to start chapter 2, 1, and 2.2 today. So this is for differential equations. I'll talk about some of the problems I think are good to do. And we'll start with 2.1, which is a free body. That was my computer, sorry. Or a falling body. I say free because, it's a simple example. It's a little bit of a simplification. So Newton's second law tells us that our force is equal to ma, and we've expressed this before in different terms. I'm going to rewrite acceleration as dv dt equal to the force. And just so everyone knows, I'm going to let down be positive. So even though Earth is pulling the object down, I'm going to count that as positive. And just doing a little free body diagram. This is why I call it a free body, because it's only subjected to gravity. And we'll call it a simple drag. Now, we've talked about linear drag in the mechanics playlist, but we're going to just do... or we've talked about quadratic drag, but we're just going to do linear. Even though this isn't exactly the best example for, like, bigger objects, but we'll stick with that just to keep things simple. Then Newton's second law tells us mass times acceleration is equal to the sum of our forces. And drag is pulling it up, so that'll be our negative. And this really gets us into our first real technique for solving differential equations. So it's called separation of variables. It's very common to be able to use this technique to solve pretty simple differential equations. And I'm just going to work through this example, and then I'll talk about it in a little more detail. Essentially, separation of variables is when your variables, in this case v and t, can be separated on different sides of the equation. So for example, I would divide both sides by this. I could divide both sides by m. We also can treat the dv and dt as differential, so I can multiply those over. If I do that, I get 1 over mg minus bv dv equals 1 over m dt. So I divided out those things in green to get them on the other side, and I multiplied over by dt. And I kind of jumped the gun here, but the trick is, once you do this, you can simply integrate both sides. I'll go ahead and pull out some constants there. And when you integrate this, you will get minus 1 over b, the natural log of, and I'll do absolute values, mg minus bv. So hopefully you're okay doing a integral with the 1 over your variable, equals 1 over mt plus c. Draw that t a little nicer. So the c is the constant of integration. They both give you a constant, however, c is just the total of those two constants, the addition of them. So I'm just keeping it so we only have one to worry about. So you can multiply over by minus b to get the natural log by itself. And we'll do minus b minus bc. And obviously we can raise this to the power of e to get rid of the natural log. The whole point is to solve for this v. That's the whole goal here. Oops. So you have e to the minus tb over m, e to the minus bc. Or I'm just going to call this ae to the minus bt over m. A, in this case, is just this series of, it's a constant. So I'm just writing it in a way that's a little bit easier. Okay. So once you have that down, you're almost done. You can subtract over by, or you could just add over BV, divide by it, or move over your constants, solve for V. So I'm just going to do it all in one sweep step. Hopefully you're okay with the algebra. mg over b minus a over b e to the minus bt over m. Okay, so this is called our general solution. It's a solution because we solve for our v, but it's general because we don't know what this constant of a is. Now, if you're giving an initial value, and this is then an initial value problem, you can solve for that. So if we say v of 0 equals v naught, in other words, at time equals 0, that's just your initial velocity. Well, then you can plug that in for t, and our v is equal to v naught, so you would have v naught equals mg over b minus a over b. E to the 0 is just 1, right? So that's just that. So you get this term of mgb minus a over b. So that you could think of as being your initial condition. And now a, oops, didn't mean to use that. Now a can be solved for. A can be solved for. So you can solve for a by simply subtracting over and multiplying by minus b. And then when you get your a, you can then substitute this a into here. So all you had to do is, you could do like a over b equals mg over b minus v naught as an example. You could multiply over by the b, plug it in. I'm going to go ahead and just plug in our values. So you get mg over b minus v naught minus mg over b e to the minus bt over m. Okay? So that's good. That is our, this is now no longer our general solution. This is our exact solution. It's exact because it's for this specific initial value. So I skipped the section where they talked a little bit about initial value problems because I didn't feel like it was so crazy that it couldn't be touched on. But that's essentially what the initial value is. So this uses, like I said, what's talked about in 2.2, which is separation. Or I guess they call it just separation of variables. Okay. So this is a, let's say you have a derivative equal to some function. If you can write this with separative, with your variable separated, so a function of y dy equals a function of x dx, then this method is very useful. Okay, so that's kind of the idea. You might see it like this: dy dx equals g of x p of y. So you just have a function of x and a function of y, completely isolated. And essentially the example we just did is an example using separation of variables and using initial value, in this case for a falling body. Okay, so that's really all separation of variables is. It's one of the easier ones to do. I'm going to go ahead and give some problems that I think we should work on. Like I said, I'll do some of these. We'll start with problem 1. This will be for the next video. Seeing if separation of variables is a valid technique for that. 11, kind of similar to what was done, but it's a little mathematically trickier. 21's a little tricky and it has an initial value, so we'll do an example with that. And the two big problems are the mixing problem and Newton's law of cooling. Both a little more challenging word problems. So I think those are good to go over. So those are going to be the 1, 2, 3, 4, 5 problems to do. I'm going to try to do a video and upload a solution for it later. But not too bad of a section. After I do that, we'll move on to, I believe it's integration factor next. So hopefully this